speaker is Rian Koots. We'll continue to solve problems. Yes.
Okay. Hi, everybody. My name is Ryan. Just an introduction. I'm Jesus' graduate student. Today I'll be talking about the direct recombination of halogens and sulfur. So first I'm going to start with a simple definition that I'm sure everybody here knows, which is just a three-body recombination of atoms, where three atoms combine to form a diatomic molecule at some three-body recombination rate constant. So our goal is to calculate this rate constant for various systems. And so the typical way that chemists and physicists have used to find these rates is through two-step mechanisms, as we saw from Robert Forey's talk yesterday, where first two atoms collide to form some metastable complex, and then a third body comes in to stabilize that molecule, and then master equations are used to calculate the K3. An alternative approach is to just simulate directly three atoms colliding and see essentially what comes out, how often these molecules are formed. And we do these simulations classically. And so this direct mechanism is what I'm focusing on today. Okay. And three-body recombination appears in all facets of physics and chemistry, from cold and ultra-cold chemistry in the lab, all the way out to super hot plasmas and atmospheric physics. So just to highlight some results from this direct method, Jesus and students have characterized ozone formation relevant to atmospheric physics, as well as super cold ion atom-atom collisions. And today I'm going to be focusing on the work that we did for sulfur recombination, which has relevance to the great oxidation event. So it's suspected to be responsible for the oxygen that our atmosphere has today, as well as any other sulfur-containing atmospheres like hot Jupiters or exoplanets. And then I'm going to talk about halogen recombination, which has some historical significance in the three-body recombination world. It is one of the first systems experimentally studied three-body recombination. Okay, so this is going to be the structure of my talk. First, I'm going to discuss the method of the direct three-body recombination with classical trajectories. And then I'm going to talk about the sulfur and halogen recombinations. First, I want to discuss the reactive cross-section, which is essentially where all the difficulty comes in describing three-body collisions. So the reactive cross-section in a two-body collision, is defined pretty simply. When you have two bodies colliding in 3 dimensions, you have this trajectory axis, and then from that trajectory axis, you can define an impact parameter. And so with this impact parameter, you can generate a space which is essentially the effective area of collisions, and then we call that a cross-section. And then from the cross-section, we can get our rates. However, when you go to a three-body case, things get confusing really quickly. There's no trajectory axis, as in the two-body case, to define an impact parameter, and therefore it's difficult to describe or define a cross-section. So the way we do this is by moving from the three-dimensional space to a six-dimensional space. And the reason we do this is because in the six-dimensional space, we have a really easy expression for the recombination cross-section. So I'm just going to briefly go over how we do this transformation and why. In the three-dimensional case, we can define these relative coordinates, as many of you probably know, the Jacobi coordinates. And so using these Jacobi coordinates, we can define a Hamiltonian and then do classical dynamics on it. With the Jacobi coordinates, we only have two vectors. The center of mass vector is stationary, and so we have 6 degrees of freedom. And that's why we define our collisions in a 6-dimensional space. And so to map from 3 dimensions to 6 dimensions, we define our position and momentum according to the 3-dimensional Jacobi vectors. And so we have these 6-dimensional vectors where we can define a Hamiltonian, which describes just one particle traveling towards some center of our coordinate system in 6 dimensions. And so once we have this scheme, we have an impact parameter, which is a 5-dimensional space, however you want to think about that. Regardless, we have this nice integral that we can work with. Okay. So the first step is to generate our initial conditions in 6D space, and we do this randomly. So our method is a Monte Carlo method. So we randomly generate our initial conditions so that we sample all of the available trajectories for our system. Next, we move back into 3 dimensions using our map to solve Hamilton's equations of motion, so everything is purely classical. And then we can calculate our cross-section by just calculating the probability of a reaction occurring given these initial conditions that we've randomly generated. And also, this depends on the collisional parameters, such as the collision energy and the impact parameter, which we define ourselves. Okay, so here's a little movie of a solution of a 3-body collision. So the 3 bodies come in, they collide at some center, and then some diatomic molecule is formed. On the bottom here, you'll see these pretty often. These are trajectory plots where they meet, and then we see a molecule formed. And so we can define our opacity, or the probability of a reaction to occur, by just counting the number of recombination events in our simulations divided by the total number of trajectories that we run. And then we stick this into the integral and calculate our cross-section. And from the cross-section, we can calculate our rates. Okay? All right, so that's the first part of the talk. Next, I'll discuss how we applied this to sulfur recombination. Now, the reason that we're interested in sulfur recombination is because of the mass-independent fractionation of sulfur. So sulfur has 4 natural isotopes, S32 being the most abundant naturally. And so geologists have defined essentially a mass-dependent fractionation, which is the normal behavior of sulfur isotopes as they relate to S32. And so for most rock samples, modern rock samples, they exhibit this behavior, where delta 33 is about half of delta 34, and this is considered normal. However, the deviation from these constant values are given by this capital delta, and that's the mass-independent fractionation. So it still depends on mass, it's just anomalous behavior. Okay, so here's a plot of the mass-independent fractionation of delta 33 versus the age of rocks that geologists have dug up. And the most surprising feature of this plot is that rocks that are over 2.5 billion years old exhibit massive mass-independent fractionation, and then any younger rocks basically don't exhibit this behavior. And so this became the most compelling evidence for the great oxygenation event. Basically, the way that these two are related is, over 2.5 billion years ago, oxygen wasn't the dominant gas in our atmosphere, or it wasn't even present. Sulfur was very dominant, and so they were free to react in the atmosphere and create these isotopic differences. And eventually, they fell into the ground and show up in rock samples. However, the molecular mechanism behind the sulfur mass-independent fractionation is still unknown. And there are essentially 2 schools of thought leading to this mass-independent fractionation. So back when, in the Archean atmosphere, there was no oxygen, and sulfur-containing compounds were released into the atmosphere through volcanic gases. And so these sulfur-containing compounds were free to react And certain reactions could lead to this MIF, or mass-independent fractionation. So one school of thought is the photodissociation of SO2, where some SO is dissociated, and then it falls into the ground, and then these mass-independent fractionation signatures are present. The other method is through the chain formation of S8. So essentially, you have this sulfur atom here after photodissociation of SO2, which leads to S2, and then S4, and then S8, and then it becomes heavy enough to drop into water and form these rocks. And so we're going to focus on the chain formation of sulfur because it has three-body recombination reactions, and that's what we do. Okay, so this S8 is essentially formed through a step of three different three-body recombination reactions. And so we're going to focus on the first of these reactions as a first step and see if we can characterize these recombination reactions, three-body reactions. Okay, so the first step is to define our interaction energy across sulfur. We take our three-body potential as an approximation, as a sum of three two-body potentials. And we define these two-body potentials as Leonard-Jones potentials. And these are relatively simple. They allow us to calculate things pretty fast. And the most important thing is that they capture the two important features in three-body recombination events. That is the long-range interaction, the 1 over r to the 6, and the dissociation energy, which defines essentially the energetics of the reaction. Okay, so here are some results. On the left, we have the opacity function as a function of the collision energy and the impact parameter. And so we see that we can populate this space under this curve, which gives us the maximum impact parameters for our system. And then this white line is just the dissociation energy, which dictates essentially the energetics, right? So we can take this opacity function, integrate under this curve, and calculate the recombination cross-section. And then we can take that, multiply it by the collisional velocities to calculate our energy-dependent recombination rate. Okay, and so here's the result of the energy-dependent recombination rate. And this vertical line here is the dissociation energy of SAR. And these dissociation energies of a system delineate essentially two interaction regions. We have the low energy regime and the high energy regime. In the low energy regime, we always see this power law behavior for the recombination rate. And then once we get to large enough energies that we surpass the dissociation energy of one of the molecules, we see a drastic decrease in the recombination rate. And so this is typical of pretty much every system that we study. Excuse me. Now, if we want to compare with experiments, in the real world, we have temperature dependence. So we convert our energy-dependent rates to a temperature distribution using Maxwell-Boltzmann distribution. And so here's just one example at 300 Kelvin. And so then we integrate under this curve for each temperature. And then we can define a temperature-dependent rate over some range of temperatures. Now, for the sulfur recombination, we only have one experimental data point given by black here. And our results are given in blue. And so we see as good of agreement as we can get with this one experimental data point. And I also put some other attempts to characterize the sulfur recombination, specifically the principle of reversibility, which is given in this red, where the reverse reaction was calculated, and then the reverse reaction of that, which is this reaction, was calculated. And that's the results here. And then this is through the energy transfer mechanism. So these two methods they also have pretty good agreement, but we see that the direct three-body recombination method also works. The next step, so this S plus argon is not a step that exhibits mass-independent fractionation, so we won't see it in this specific case. We tried, but as expected, we didn't see it. However, this three-body recombination collision is expected to lead to mass-independent fractionation. So changing the isotopes of this sulfur here should give different signatures in our rates. And so we eventually plan to extend our theory to allow for atom-atom molecule collisions, which is still a three-body collision, except one of the atoms is a molecule with internal structure. And then we can create these three-atom molecules, S3. Okay, so that concludes the discussion on sulfur recombination. Next, I'll talk about the halogen recombination. So in the 1930s, Rabinowitz and Wood published these two studies on the kinetics of recombination of iodine and bromine atoms. And so these were, I believe, the first experiments to study three-body recombination, where they took these iodine and bromine atoms in bath gases, various bath gases of noble gases, and they attempted to characterize the rates of these three-body collisions. Now, this work continued all the way up until about 1980, and I highlight these two papers because they're a series of 8 papers that essentially was the final theoretical study that attempted to characterize these collisions. And they used the energy transfer and radical molecule complex two-step mechanisms to define these collisions and rates. But we wanted to take our approach and see how well it does for these halogen recombination systems. So we use this direct method and compare. Again, the first step is to calculate the potential energy curves. So we calculated them using CCSDT. And so for each system, here on the top we have iodine, on the bottom we have bromine. And then we fit our calculated potentials to, again, our Leonard-Jones potential, because things are just easier and accurate enough to describe our collisions. Okay, so once again, this is always our main result, is the energy-dependent recombination rate coefficient. And again, we see this typical behavior of power law in the low energy regime, and then a drastic decrease. On the top we have for iodine, bromine, so on. Now, before we go on to compare with the experiment, we have to consider a couple of things. All these experiments were done using pump probe techniques, which means once the molecule is created, they don't observe it immediately after it's created. It continues to collide with other molecules in the chamber. And typically, the products that are formed by three-body recombination are formed in really weakly bound states. And so they're susceptible to being dissociated, which goes off as the temperature of the gas. But they could also, get de-excited into more deeply bound states. And so we have to attach this survivability factor so that we can compare with the experiment, which goes off as 1 over the temperature. So the hotter things get, the less likely it is to survive. And it also depends on this delta E. Now, this delta E is just the average energy spacing of these bound states. And so we can calculate this delta E by looking at the bound states that are bound by the long-range potential, so given in this dash here. And so we find that the average energy spacing of these molecules for bromine specifically is about 210 wave numbers. For iodine, it's about 150. Okay, so now I've defined this survivability factor and why we use it. We also consider the degeneracy of these halogens. And this was considered in all of the experiments as well, so it's a direct comparison. Essentially, when you have these two ground bromine atoms colliding, their energy levels split into a total of 16 different combinations, 4 for each, and 5 of which are attractive. So we consider only the attractive states in our system, and so we attach this G and this survivability factor and multiply it by our temperature-dependent rate, which is obtained in the same way that we calculated for sulfur. And then we get this recombination rate constant. Okay, so now we can plot our temperature-dependent rate constant for iodine and bromine. And here I just plotted for iodine with argon and bromine with argon, because that's where most of the experimental data across various temperatures exists. And these data were collected over, say, a period of 40, 50 years. And so we have our blue curve, which is our results through the direct three-body recombination. And we find pretty good agreement with the experimental results after we attach these factors, of course. And so I also compare it to that 1980 paper of Burns, which is the final study, the final attempt at characterizing these collisions. And so they define both the energy transfer mechanism and the radical molecule complex mechanism, and then they just combine it to form their rate. And they also get pretty good agreement. It'd be interesting to see today's treatment of these two-step mechanisms, which has obviously evolved since the 1980s, and see how well it does here. But we didn't do that. Next step is to just take a look across all different systems and see how well we do, as the noble gas varies. And so most of the data for all these other noble gases were taken at room temperature. So we just slice it right here at 300 Kelvin, and then we plot our recombination rate, theoretical recombination rate at 300 Kelvin against the third body. So we get pretty good agreement across all different systems. Notably, we capture the dependence on the third body. As third bodies get heavier, the recombination rate increases. And it scales accordingly to the experimental values, which is great. However, we see some pretty big discrepancies right here, which is the system of iodine and helium. So let's take a closer look at that. So here's the temperature dependence for iodine with helium recombination. And yeah, we're pretty far off from the experimental data. But, I guess the saving grace is that we capture the right temperature trend. So that still gives us confidence that we're doing the right thing. We're just off by some factor that we didn't consider. And again, we have these energy transfer, RMC, and the combined values, which were calculated in the 70s. We also have this black curve, which is calculated in the final paper, the 1980 paper, where they see this dip at low temperatures. And this is pretty typical of the two-step approach, is that it drops at low temperatures. And so to address this, Burns wrote, one important conclusion of this work is then that the ET mechanism, the energy transfer mechanism, so when the third body is light, the ET mechanism is said to dominate. Accepted in literature for a period of 40 years, constitutes a doubtful approximation and should be used with care. Whenever the ET mechanism predominates, it would seem more appropriate to substitute it with a more rigorous three-body problem solution. And so this is essentially one way that we'd like to use this more rigorous approach, I suppose. And so, yeah, we're doing pretty good as far as the temperature dependence goes.
Can I ask a question?
Yeah.
Yeah, so I assume the ET mechanism here is the resonance, and it's using the same Jacobi coordinates that you're using in your direct calculations. So why don't you just add the ET curve there to your curve, and then you'll get much better agreement with the experiment?
Yeah, I suppose. I guess we just wanted to keep it, we just wanted to identify the role of just the direct recombination without considering any other mechanisms.
Right, and I would not add the RMC because that's a different Jacobi coordinate system. And so I think the two that you want to add, not the RMC and the ET, I think the two you want to add are the ET plus your direct.
Okay. Yeah, that actually might make sense. We didn't consider that just for the fact that we wanted to look at that, but that actually probably would work. I only put these RMC plus ET because this was the approach that the authors took in the 70s. But yeah, that would work. I'd have to think about that, I guess. Yeah, thank you for the suggestion, though. Okay, so I guess I've talked about everything I wanted to talk about today. So we have this general prescription for classical three-body recombination, and it can be used in almost any situation where three-body recombination occurs. And because they're classical, they can be calculated very quickly, very simply with simple potentials, like we have the Leonard-Jones potential, and we can still capture pretty accurate results. And so whenever you have a three-body collision, it might be a good idea to try this out first before you go into your quantum scattering calculations to get super accurate things, just as a preliminary check, because it's very quick. So yeah, using this approach, we've developed an accurate description of a sulfur recombination, which is relevant for modeling of Earth's early atmosphere, or any sulfur-containing atmospheres. We've also identified the role of direct three-body recombination in halogens, which still needs a little bit of work regarding light atoms like helium. Okay, so all these results were run on the Pi3BR, which is the code hosted by me and Jesus. And it's available, it's open source, so you guys, if you're ever looking into a three-body recombination reaction, you can just download this, run your calculations relatively quickly, and just take a quick look at what your system looks like. Okay, oh, sorry. All right, just a shout out to the rest of the group. Thank you, Jesus. Thank you, everybody. All right, thanks for listening.
Beginner's question, I guess. So you started out explaining, how you work in this six-dimensional space, and scattering we know from two-body scattering, and then you have the impact parameter B. But of course, what is really helpful is that we have this rotational symmetry normally. For you don't have to care about the angle.
Sure.
And so now I wonder, in your six-dimensional space, in how far are there symmetries like that too, or is it more complicated?
Yeah. So when we define this hyperspherical coordinate system, it's defined by one radius and 5 hyperangles, right? So these angles are chosen randomly from a distribution, probability distribution. I don't have all the equations, but essentially we have this coordinate system, and then we randomly sample each of the angles according to different probability distributions. So yeah, to answer your question, yeah, it does get pretty complicated. Yeah.
here. Yeah, you just have an integral over B.
Yeah. I guess I didn't want to add a lot of equations. But yeah, so the angles are randomly sampled. Sorry, does that answer your question? Okay, thank you.
How do you distribute the energy in the beginning? What about angular momentum energy? Kinetic energy in the beginning, and all these momenta do not play exactly the same roles. So what is it?
Yeah, so first we define our collision energies in the code, right? So that's our initial conditions. And then the momentum is I believe, well, actually it depends. So depending on our system, so we define the momentum just through these two Jacobi vectors. That's a good question.
What is angular momentum there? It's very tricky.
The angular momentum? Well, I mean, I guess in the six-dimensional case, there isn't really an angular momentum because you just have one particle going into the center. Okay. Okay, yeah.
I mean, when you sample over the momentum and the impact parameter, you're sampling over angular momentum at the same time. So you don't have to do it separately.
Yes.
Thank you, Chris.
Actually, I was curious about this survivability factor. I didn't really understand physically why the energy density comes into that. The average energy spacing. Why is that a relevant quantity?
Well, okay, so essentially it gives you the likelihood of the molecule dissociating, right?
I guess I don't see why.
Well, I guess the more weakly bound you get, the smaller the energy spacing gets, and that dictates, I guess, your survivability.
Yeah,
Yeah.
I guess I was expecting the binding energy over kT, not so much the average energy spacing.
Well, this is to.
This is indeed what's happening. The only thing like here we have such a huge density of bond states that this is what Jordan Trow proposed in the 70s. He proposed this delta E, and this is what he used also for ozone formation. So this is similar to what you presented yesterday about the thermal correction that you did, guys, but you only have like 3 states, right?
Yeah.
Here we have like 20 or 30, so we have to do some kind of average. That's the idea that Trow proposed, and is the boundary.
Oh, is it an average binding energy, or it's not an average spacing? I thought you said average spacing, average density of states, but it's actually an average binding energy.
Yeah,
Okay.
yeah, it's like kind of.
Then that makes total sense.
Sorry.
This is what Jordan Trow did in the 70s.
Okay, thanks.
He did that.
I got it.
I was going to ask the same question, but maybe just to extend the survivability factor. Is there a rigorous foundation for that, or is that just something that you just tack on, in order to get it agreement with the experiment, like a fitting parameter or something?
Yeah, I mean, we have to account, so these calculations are of the nascent products. So immediately after they collide in an isolated space, we need to account for the fact that these molecules won't survive in an experiment as they're created. They change by the time they're measured. And so this is just one way to represent how they change from the time that they're created to the time that they're measured.
Right, and I think Trow used like a master equation study to suggest this, but does that transfer from one system to the next? You're just using it?
Well, it depends on which experiment you're going to compare with, yeah. It depends on the experimental technique. In this case, they're pump probe techniques in gas chambers. So this is why we did it.
Okay, but is there like a real picture associated with it, or is it just something that?
Yeah, it's just it's a statistical approximation. Yeah, it's not. I guess it's not the most rigorous approach, but it captures the right temperature dependence. So that's why. Yeah, that's why we do it. Yeah.
I have one more question. So you were talking about, the history, how oxygen came about and the sulfur sulfur was kind of, falls out of the sky and then into the ocean. So is there at a particular level in the ocean, is there a sulfur layer really that one can, 2 million years ago, there must have been, if that happened around that range, I would guess that there should be a layer.
Yeah.
Where we find, a lot of sulfur.
Well, so those rock samples were actually taken from a canyon, but there used to be a lot more water on Earth. So yeah, essentially, it's not really in the ocean anymore. I'm not sure. Yeah, that's a good question.
That's my question. So how can you, how can we be sure about the story?
Like the age?
Find that, represented somehow in rock formations or on the bottom of our oceans.
Yeah. So. So yeah, I mean these are. I guess that's the work for the geologists, right? They sample these super old rocks and they age them, and then they do their elemental studies on them. But yeah, I'm not too sure exactly like how the structure of the rock works. I think I guess the deeper you go, the older they get, right?
Yeah, I mean there must be a layer, I guess, coming, representing a certain time.
Yeah.
These things were
These
deposited.
samples were taken in Australia. In Australia, there is a rock formation. I was reading about this thing. It's weird. So in Australia, there is some kind of rock formation where they found the first stromatolites, which is the first living organisms in the history of human. Well, not humankind, history of life, right? And then they start to dig up. Like 1 kilometer down, and then they found this evidence. So this is coming from Australia, and there is another one in South Africa. So now has been confirmed in 2 different parts of the world. Not in Ulm, not in Germany, okay? No worries, you're fine. You are not going to find anything in Germany. I don't know why it's only South Africa or Australia for now. That way I can tell you, but we can talk later.
Well, we have to keep digging, I think.
Dig a hole.
Another sort of continuation of this question. So you compared with the experimental results. So there's a single experimental point on this sulfur combination.
Yeah.
But it's supposed that there is some condition that you need to satisfy in order to trigger this great oxidation event. So the question is how your calculation, for example, they predict what temperature should be in order to trigger such an event. Can you compare that with some sort of thoughts from the other.
Well, by event you mean the great oxidation event?
You show the temperature dependence of your three-meter condition, so I suppose that you need to satisfy some temperature condition to trigger this event. To trigger, right? So you produce on the first step of this recombination event.
Sure.
I suppose that it was triggered by something. Right? So you show that it was triggered by.
So here, right?
Okay, after this certain change. So
Yeah.
Can you say something about, can you predict something regarding the necessary condition in order to start this great oxidation event, or it's not?
Yeah. I mean, so the reason why they think that this is evidence for the great oxidation event is because in an oxygen-free atmosphere, these sulfur atoms dominated. And so they were free to do these reactions. Nothing really triggered the reactions. Essentially, what triggered, what was the trigger was the stopping of these reactions, this is essentially when these reactions are suspected to have stopped in the atmosphere. When the atmosphere was populated by oxygen and sulfur was no longer present. So yeah, this would be the trigger, essentially, is the rise of oxygen, which people are still debating on what the cause of that is, but I guess through anoxic life forms, I guess, is the leading theory.
So you cannot sort of give some insight into this question with your calculations?
No. I guess it's useful for essentially that would require the modeling of an entire atmosphere, which needs the rates that we calculated. So the reason temperature dependence is useful is because let's say the temperature of the Earth's atmosphere wasn't room temperature, it was some other temperature. we have those rates as well. Yeah.
There are no more questions. Then let's thank the speaker again.
Thank you.